So I will continue speaking about a similar thing that we just heard in the nice talk by my mic. So what I will present is a... oh, now I see your emails again, but I will not look. So what I will speak about is another way of implementing numerical approximations to Calabi-Yau metrics using machine learning and using a slightly different architecture of the neural networks than we heard about in Mike's talk. It's fine.
Don't read them. Yeah.
I will not read them. And this is work done in collaboration with Andre Lucas, Fabian Rule, who is here, and Robin Schneider, who is a PhD student in Uppsala. And I would like to say already from the start that I should really highlight Fabian's and Robin's work here because they are the ones that have written the code that we're using, and they have done a really great job on doing this. So this has been published in a paper from late last year, and there is also some work in progress that I will report on today. So we've already heard in Mike's talk that machine learning is an interesting tool to use in string theory. And in addition to the topic that we have talked about today, that is learning the Calabi-Yau metrics, they have also, these kind of tools have also been used to construct and study interesting compactifications in string theory, for example, look for interesting solutions in the string landscape, to probe questions such as the swampland conjectures, so for example, the distance conjecture, computing eigenvalues of Laplacians and looking at various, how these things evolve as you go to various limits in moduli space. They've also been used to study geometry, so to predict and compute topological properties of Calabi-Yau manifolds. Now, this is something that in principle we know how to do using algebraic geometry methods, but what machine learning then offers is a faster way and maybe a more economic way of doing this, which can allow us to study more complicated geometries. And also, they allow us to approximate the Calabi-Yau metric, which is the topic of this talk here. So as we just heard in Mike's talk, we do not have an analytic expression for the Calabi-Yau metric, so this allows us to go beyond what could be done before, and it complements previous numerical methods and gives some extra power to those. So why would you want to do this? Well, Calabi-Yau manifolds, as we have heard in this conference, is our pet geometries in this field. So we like to use them. We know a lot about Calabi-Yau manifolds, and we can construct them in great numbers. So there are extensive lists of examples where we can try and test our tools. And in this talk, I will talk about two types of Calabi-Yau manifolds, the CCs, the complete intersection Calabi-Yau manifolds, which are intersections intersections of hypersurfaces in projective spaces. And I will also talk about Calabi-Yau hypersurfaces in four-dimensional toric ambient space, and I will refer to those as the Kreuter-Skarke Calabi-Yau manifolds because they are associated to the work of. Kreuter and Skarke have given us the tools to construct such examples in a very nice database of toric polytopes. So the metric is interesting in string theory because it allows us to, or it shows up in couplings and masses in low-energy effective field theories arising from string compactifications. They can, as I've already mentioned, be used to test swampland conjectures, and they can also be used to probe various mathematical properties in geometry. So, for example, the SYC conjecture in mirror symmetry is something that would benefit from knowing what the metric is in order to be explored further. And also, over the past years, as we have heard, there has been machine learning success in predicting metrics on example Calabi-Yaus. And in particular, there's been a lot of focus on one-parameter Calabi-Yaus like the quintic. And here is a number of papers on that, on these topics, and I apologize if I have forgotten any reference here. So in this talk, what I will do is that I will present for you the work that we have done and where we are now in the process of learning metrics on different kinds of Calabi-Yau manifolds. So what I will tell you is that we can now machine learn metrics on a diverse set of Calabi-Yau manifolds. In principle, we can compute the metric on any manifold from the CC or Kreuzer-Skarke list. We can do this with multiple complex and Kähler moduli. And what this, the challenges that this brings about is that with these multiple Kähler moduli, we need new procedures to control the Kähler class so that we know that the metric that we're learning, the Ritchie flat metric that we're approximating, that this is in the same Kähler class as the reference metric that we started with, or that we have control of which Kähler class this is in. And also for these toric ambient spaces, there was a need for new procedures for sampling points in a good way on these ambient spaces. So that was not available until our work, or at least not as far as we know. So let's go back to the basics then. So what do we want to do? Well, we have the Calabi-Yau theorem, as Mike has very nicely reviewed it already. So we know that for any compact complex Kähler manifold that has a holomorphic top form and a real close to 1,1 form, we can construct, we cannot construct it, but there exists a unique Ritchie flat Calabi-Yau metric, which is in the same Kähler class as a reference, this reference Kähler form that we know exists. And this unique Calabi-Yau metric and the associated unique Calabi-Yau Kähler form solves the Monge-Ampere equation, which I've given here. So if we wedge for a threefold, if we wedge this Calabi-Yau Kähler form with itself 3 times, then this would give us a volume form on the Calabi-Yau, and this has to be proportional to another volume form, which we can construct from the holomorphic top form, which we know how to build. So if we can solve this Monge-Ampere equation, then we have found the Kähler form that is associated to the Calabi-Yau metric. So this is the task that we set out to solve then with the machine learning tools. Now for the Calabi-Yau manifolds that we know how to construct, and in particular for the CCs and the Kreuzer-Skarke Calabi-Yaus, we know how to construct the holomorphic top form. We compute it by a residue formula. And we know how to construct particular types of Kähler forms on the manifold using information from the ambient space. So in a way, the point of these constructions of Calabi-Yau manifolds is that we are constructing these complicated geometries inside simpler Kähler spaces. And then we're using that as you are looking at solutions to some polynomial equation inside a Kähler space. You will also get a Kähler space. And a Kähler form will be inherited just using restriction to your Calabi-Yau of the Kähler form of the ambient space. Also, as already said, in general, there's no analytic expression for this Calabi-Yau metric that we're after. So naturally, then, people have tried to explore this using numerical methods. And I don't think I need to say a lot here because we had a very, very nice summary of this in Mike's talk. So let me go on and describe what we do in our work. So what we do is that we use a package, which is called CY metric, and which you can download and use yourself. You can find it on GitHub. And this CY metric is a machine learning package that decomposes into 2 pieces. One is a set of point generators, which are based on the Schiffman-Seldish theorem, which I will describe a bit towards the end of the talk. And then there are custom TensorFlow neural networks that predict the Calabi-Yau metric at a given point in moduli space and using the information from these point generators. So pictorially, what we have here is that we are generating some points, and then we are feeding those points into a neural network, and that should give us information about the Calabi-Yau metric. So let me say something about the point generators before we go into discussing the neural networks. So the natural attempts you might think of directly when you want to generate points is that you just want to sample things randomly on the ambient space. And this is in principle what we do. But we need to be a bit clever in doing this, Because if we just take some random values of points on the ambient space and reject all those that are not in the Calabi-Yau, then we will reject most of the points because the Calabi-Yau is just a hypersurface in the ambient space, so it's of low codimension. It's a low-dimensional space in a high, and it has high codimension. And also, if we would just maybe try to be a bit more clever and pick some random values of ambient space coordinates and use the defining polynomials to solve for the rest, then that will introduce a bias in the way that these points are sampling, and it will not give us good random distribution of the points on the ambient space. Now, luckily for us, this problem was almost completely solved before. And so in particular for complete intersection Calabi-Yaus, there were algorithms developed by Mike and others that sample these points in a good way, giving us an information about how the points that we get are distributed on the Calabi-Yau that we are interested in. So on the Calabi-Yau, this intersection of hypersurfaces in this complete intersection, in this product of projective ambient spaces. Then for the Calabi-Yau hypersurfaces in toric spaces, this was not known, and we generalized it, and I will describe it at the end. The reason why I wanted to talk about this at the end is because this is not really a machine learning problem, but so I wanted to talk about the machine learning first, and then I will come back to the point generation. So for now, what I want you to take as given is that we have a good way, and an efficient way, I should say also. It's a relatively fast way of sampling these points, to get points that have a good distribution on the Calabi-Yau that we are interested in. And then we will come back to the problem that we want to solve now. So now what we want to do is that we want to solve this Monge-Ampere equation, and we want to use a neural network for that. And we should recall that we have information on the Calabi-Yau, so we have the sample of points, which are randomly distributed with respect to a known measure. And also, we know what the holomorphic top form is, and we know we have a particular Kähler form, which I will refer to as the Fubini-Studi form, that's what the FS is for, such that we know that the Calabi-Yau Kähler form that we're after is in the same Kähler class as this Fubini-Studi form. So the plan then is to use this point sample, feed it into a neural network that we will train and test using our physics knowledge, and then get the metric prediction out from this. So are there any questions so far? Maybe I should ask. Good. OK, so neural networks, what are they? We have already heard from Mike, so I can be rather brief here. So what we have is a collection of nodes that are connected with in various ways. And the way that they are connected are determined by certain parameters that are associated to the nodes, which are called weight and biases. So what the user sees then is the input layer and the output layer of the neural network, and then there are a number of hidden layers in between that the user does not have access to, but that will be updated in the course of training the network. We are using a simple feed-forward neural network because of the good performance of such networks on the problem at hand. And the parameters of these networks are updated via stochastic gradient descent. So this is the sort of back and forth iteration of what's happening, of how data is transmitted in the network that Mike was talking about. And the idea is that so the network is working, the way that the network is trained and the way that the network is updating its parameters is with the objective of minimizing certain loss functions. So the way that we tell the network about physics is to give it these loss functions, and this I will come to in a couple of slides. Now, as a user, if you were to use this neural network, what you can control is a bit about the simple features of the architecture of this network. So how many hidden layers there are, how many nodes there are in each layer. This is known as the depth and width of the neural network. You can also control things that are related to the stochastic gradient descent methods, so the batch size. You want to compute, when you're looking for minimization problems, computing gradients on a huge number of points is very expensive, so you batch your data into smaller bits, into smaller batches, and you compute your gradients on those. That speeds up the process and makes it also more stable as a method. You can also choose these activation functions that we heard about in Mike's talk. So how fast the network wants to learn, and then there are other parameters that you can tune. In addition to this, we have set up a neural network where you can also choose which ansatz of the metric you want the neural network to use. So we know that the metric should be a Kähler metric, which is associated to a Kähler form, which lies in the same Kähler class as the Fubini-Study Kähler form. So what we can tell so we can then give the neural network more or less information about what kind of function it should look for, or what kind of metric it should look for. So either we could tell it just to go and look for any metric, not feed any information into the ansatz of the metric, so that would be what we call the free model, or we could give it some information about the fact that we believe that the metric that we're looking for is some correction to the Fubini-Study metric that we already have. So this would be these kind of models here. And in the final one here, the phi model, which is highlighted in blue, we're giving it the most information that we can. So here we're actually saying that you should look for corrections to the metric, which is given as this particular in this particular form, and you recognize this from the Monge-Ampere, from the fact that the metric that we're looking for is in the same Kähler class as the Fubini-Study metric. So here we have an exact addition to the metric, provided that phi is a function, of course. So what are the benefits of these different ansatz? Well, the point was that we didn't quite know at the start of the work, or we had some indications from previous work by Fabian, but we wanted to explore these different features, and we want to make them available, also to have a network that could be adapted to other kinds of problems. Maybe you want to look for some other metric on the Calabi-Yau that is not Ritchie flat, but has some other features. So then having these kind of options here is good. So that's the setup for the neural networks, and these are things that can be chosen in the nice package that Fabian and Robin have written. So then we want to give some more physics knowledge and some more math knowledge to the, maybe I should really say math knowledge, to the network. And this we do by a bunch of loss functions. So these are functions that guide the metric's evolution. And they encode the various equations that we want to satisfy. So there are 5 of them in the current implementation of CY metric, and this is the Monge-Ampere loss, which is enforcing the Monge-Ampere equation. Then we have a loss which makes sure that the metric is Kähler. So this enforces DJ to be 0. And since we're feeding into we have a real neural network, so we have to, these are the real and imaginary parts of various derivatives of the metric that we're computing here. So if you think back on the different ansatz that we have for the metric, you see that if we are already choosing the phi model, then this Kähler loss will not be so interesting because it's already automatic. So depending on your ansatz, you might want to turn on or turn off some of these losses. And this you can do as a user by choosing these parameters alpha here. So that was the Monge-Ampere loss and the Kähler loss. Then we want the metric that we find to transform in the right way as we go from one patch to the other. So there's a loss associated to that, which is called the transition loss. There's a Ritchie loss, which is more or less duplicating what the Monge-Ampere loss is doing because of the Calabi-Yau theorem, but we have included it for completeness and also to see if there is some tension between these two goals when you try to solve this numerically. And then the final loss is to keep the Kähler class, and I'll come back to that in a bit and explain it in more detail because it's a bit more complicated than the other ones. So this is the loss functions that we plug into that we tell the neural network to minimize. So, okay, we do this. We let the neural network have some points on the Calabi-Yau. They are randomly distributed with respect to some known measure, and then we give it the loss functions, we set all the parameters of the network, and then we allow it to do its thing. So after it's fully trained, we want to measure the performance of the network, and we want to check how close we are to satisfying the Monge-Ampere equation, and if the metric is Ritchie flat in the end. So the way we do that is to check these two measures, error measures, which are known as the sigma measure and the R measure. And these are established benchmarks in the numerical approximation of Calabi-Yau metrics literature. So it's good to have these same kind of error measures so that you can compare different methods with each other, because that's otherwise rather hard. So what do these error measures do? Well, the sigma measure is computing. So here we have PR here for prediction. That's the output of the neural network. So this is telling us how far is this from satisfying the Monge-Ampere equation. So this should be 0 if we have a good solution. And similarly, the R measure here is a measure of, it's not the Ritchie tensor here, it's the Ritchie scalar, so it's a necessary condition to have a vanishing Ritchie tensor in the end, so a Ritchie flat metric. But it's not the full condition, so one could also look at other error measures that are associated to the Ritchie tensor. So these are then things that we want to compute, and we want to compute it for the whole Calabi-Yau, so we integrate it over the Calabi-Yau, and in order to do so, we need to have a way of integrating things that works using our numerical method. And in particular, to use the numerical metric that we have. So the way we do that is that we are using Monte Carlo integration for which, and we define it for a given function f in the following way. So interestingly, even though we don't know the metric on the Calabi-Yau, we know the exact measure when it comes to integration, because we have the holomorphic 3 form. So it gives us this omega wedge omega bar. So that is up to kappa, the volume form of the Calabi-Yau. So this is what we want to compute. We know that. But we have points that are sampled with respect to some known measure, but it doesn't have to be this measure. So then we relate the thing that we want to compute to the things that we know. So here we can compute everything. We know what this d-vol Calabi-Yau is. It's this omega wedge omega bar. We know dA because that's the measure that we know from ambient space. And then we can approximate this this integral here now by a Monte Carlo integration with some particular weights which are computed from the Calabi-Yau top form omega wedge omega bar over dA. So for every point we are computing these kind of weights, and then using those weights we can numerically compute all the integrals that we need. So in particular we can compute these error measures at the end of our training, and it can compute any other integral that we might be interested in, such as, for example, the volume integral, to check that we have that the volume is preserved under learning. Okay, so let's see how this works. So the Fermat-Quintic is the manifold that has been studied most when it comes to numerical approximations of Calabi-Yau metrics, so that is a good place to start. So we have performed various experiments on the Calabi-Yau Fermat-Quintic, and what we are showing here are the results of some of these experiments. So these are So here we have trained the neural network for 100 epochs. We have about 200,000 points. We have a particular split of our points into a training set that we train the neural network on, and a test set that we test the performance on. So what you see here in these plots is that we are checking how these various loss functions are decreasing as we are training the Calabi-Yau as we are training the neural network to find the Calabi-Yau metric. So what you see here is that this Monge-Ampere loss is is going down for all of these different ansatser for the metric. And we can see that some of them are performing better than others. That is, they are learning the metric faster. They're approaching a solution with small Monge-Ampere loss faster than others. So in particular, this red curve here shows the phi model, where we are telling the neural network that it should go and look for an addition to the Fubini-Studer metric, which is of the form del bar phi. So this is performing fairly well in all of these cases, whereas if you compare this with, say, the free model, which is where we don't tell the neural network anything about the relation between these metrics, that you see that this is also learning, but at a slower rate. So this is the decrease of the Monge-Ampere loss on the training data, and we can see that we have a similar performance on the validation data. So this is an important check of the machine learning routines, that we're not just overfitting to the data that we're giving it. It's actually learning something about the structure. And we do similar things for the other loss functions here, and I should say that, and then in the second row here, we have the different tests and measures of the performance. So we see that both the sigma measure and the R measure are going down. We have a good development for this red curve here, so for the phi model in both cases. In these runs, we have fixed the volume of the network to be 1, this sort of overall normalization, and we see that for most of the networks, it quickly approaches this constant value. Also, I should say that what is shown here in the last part is that we made a comparison between the sigma measure and the R measure, just to show that to check that if one goes down, then the other also goes down, and we see the same. And this is indeed what we see, and we find a linear relation between these two measures. So that was the kind of methods that had been studied before, and now we want to, the kind of Calabi-Yau manifolds that had been studied before, and now we want to go on and we want to look at models with multiple Kähler moduli. And there, what we need to do and what we need to care about is that we want to preserve the Kähler class. Now, the Kähler class, as we've heard in Fabian's talk yesterday, for example, is fixed by computing certain volumes on the manifold. So what we can ask is, if we can be guaranteed that this is fixed during training. And then for manifolds like the quintic, where we only have one Kähler class, this is automatic. Also, if we can ensure that our metric ansatz ensure that the correction to J is exact, this will also be automatic. But we want to explore all of these different networks, so we wanted to add a loss function that would enforce this instead. And this is then this loss function, which is called K-class, which works from all of these metric ansatz. So how could we implement this kind of loss function? Well, there are different ways we could do. We could either make sure that we fix all these different volumes for some basis of curves, devices, and then the total volume of the Calabi-Yau. But this requires now sampling points on various curves and devices, which is which we found a bit unattractive. So instead, what we went on and did was to use a basis of line bundles and compute the slopes of these line bundles. So line bundles over the Calabi-Yau have a topological property that's known as slope, which is related to the first chunk class of the line bundle. So this is something you can compute topologically if you know the intersection numbers of the Calabi-Yau. So this then has to agree for all metrics in the same Kähler class. So we can then implement this as a loss function. So if we have an H1 one-dimensional basis of line bundles, we can compute the losses of these line bundles, and we can make sure that they are preserved, or we enforce that this is preserved during the training by this kind of loss function here. So here you see we sum over this basis here, and then we are computing the topological so then we are computing the loss function with respect to the Fubini-Studer metric, which is the thing that we start with, and then we're comparing that with the loss function from the prediction that we have for the metric. And and this is computed then with some particular norm. Now, this makes sense mathematically, but it's a bit awkward when it comes to the numerical implementation, because here we need to integrate over things. So this does not make sense to compute on a mini batch, so on a very small sample of points. We need to compute it on a slightly larger section of the manifold, or a larger number of points on the manifold, so that the integral is closer to what the true integral would be. So then the code becomes a bit more involved. But we hope we have gotten it right, and then we can cross-check after training. We can compute the volume of the Calabi-Yau, we can compute line bundle slopes for different kinds of line bundles, and we can check whether this matches the exact values that we know, the topological values, and the Fubini-Studio metric values, and the Calabi-Yau metric values. So let's see how that works in an example. This is a particular complete intersection Calabi-Yau known as the bicubic, which is given by a homogeneous 3,3 polynomial in an ambient space, which is the product of two P2s. This has 2 Kähler moduli and 83 complex structure moduli. So what we will do now is that we will first choose the complex structure moduli by specifying the defining polynomial, so the coefficients in the defining polynomial of the hypersurface. And then we will choose several Kähler moduli paired with line bundles in a particular way. So we are particularly interested in seeing whether we can make sure that line bundles with vanishing slope come out and having vanishing slope in the end. So we just pick different points in moduli space, and we train the metric on these different points in moduli space, and we get then predictions for what the metric should be. Also here we run this from 400 epochs. These are some various parameters for the network. And I should also say that this is not something that takes a long time. Generating the points take maybe 30 minutes, an hour, and carrying out this training about 2 hours on a laptop. And here are the results now for the bicubic. So we have here, we see the losses again going down. Here we have what is plotted here is the sigma loss on training and test data. So training data is the darker shade of blue, test data is the lighter shade of blue. And in orange we have the Kähler class loss, which is this new loss that we were interested in. And what we can see here in these plots here is that there is, the network is learning, so the loss is going down for all these cases. Also, we noticed a little effect here, which might or might not be interesting. So if you have a highly asymmetric, if you choose your Kähler moduli in an asymmetric way, this seems to be harder for the network to be trained on that, and that is maybe what you would naturally expect. But overall, we see nice performance, and we also checked at the end then of the training whether we can compute the slope for different line bundles again, and check that these agree, comparing both the topological values, the values computed by using the Fubini-Studio metric and the Calabi-Yau metric for different choices of Kähler moduli, and we find that they do indeed agree. And we also check that the volumes agree, so the volume of the total Calabi-Yau at the end. And this is not used in any of our loss functions, so this is an independent check of the performance of the network. So we were very pleased to see that also after this rather, at least in time, short run, we could get an accuracy of our networks, which predicted then the volume with about 1 to 2% error for all these different cases. And so I should say something here also, that the Fubini-Studio metric here that we compute, it might seem a bit weird that we're computing that one too, because we could just compare the Calabi-Yau prediction, so the predicted Calabi-Yau metric with the topological value. That is basically all the information we need. But this actually checks our point sampling routines. So the Fubini-Studio measure, if this volume had came out wrong, then there would be something problematic with our point sampling. So this is also a good quality check of the way that we sample points. Which then brings me naturally to discussing how we actually sample these points. So then we will leave the machine learning part of the story for a bit, and we will talk about how do we find a good sample of points on a Calabi-Yau manifold. So let's go back and think about the simplest case. So when we have a Calabi-Yau hypersurface, a Calabi-Yau that is defined as a single hypersurface in a single projective space. Now, why is this simple? Well, the thing that is simple about this is that with an ambient space that is P4, then there are good ways of sampling random points on this space. So on any projective space, we can find a nice sample of random points basically by using one of the many methods that exist for how to sample points on spheres. So there are numerical methods for how to sample points on spheres in any dimension, and this can be translated to sampling points on a projective space. So if you have P4, you would sample points on S9, which basically means that you go to R10, you sample points on some hypercube, you scale out a couple of things, and then in the end you have points that are sampled on P4 with a known distribution, which is the Fubini-Studi metric. So this is something that is well known. And then what you can do is that you can connect two such points that are sampled on P4 with a line, which has one parameter, and you can intersect that line with your Calabi-Yau hypersurface. And for the quintic case, the Calabi-Yau is given by a quintic polynomial, so this will give you 5 points on the Calabi-Yau. And then by this theorem of Schiffmann-Selditch, which tells you the measure on how these such lines would be distributed, you know that these points are distributed according to the Fubini-Studi metric on the Calabi-Yau. And this generates to other CCs as well, and this was worked out in a very nice, this algorithm that I've shown here is due to Mike and others' work in the past. So basically, we can generate random points on PR using this connection with the spheres. We distribute free parameters in various ways. So we get hypersurfaces and we get lines and surfaces that we can intersect with the hypersurface, and then we get points on the Calabi-Yau. And this, in the CY metric package, this is implemented as one of the point generators that you can use. So on the Kreuzer-Skarke Calabi-Yau threefolds, we do not have projective spaces as ambient spaces anymore. We have a toric variety instead. So and then there are various things you can try to do, but one of the things that we can try to do is to relate this ambient toric variety to a projective space. Because if we can do this, then we can apply the Schiffmann-Selditch theorem and generalize the CC algorithm that we already have. So that gives us a good way of generating points then. So how can we do that? Well, this actually works. So if you look at the Kähler cone of a toric variety, this is generated by certain generators, so called J alpha. And what you can do is that you can look at sections of these J alpha, and it turns out that because these generators happen to be base point free and so on, it turns out that these sections behave just as the coordinates of a projective space. So they cannot all vanish at the same time, and they have a certain scaling relation. So this gives us a map then from these sections of Kähler cone generators to some projective spaces. And then we can basically, so the name of the game is basically just to use this. We map from our toric coordinates to the coordinates, so these sections, which are the coordinates then of these projective spaces. We express everything, so in particular the Calabi-Yau hypersurface equation, in terms of these sections. And we use the Schiffmann-Selditch theorem and the algorithm basically from the CCs in the same way. So we generate random points on the PRs, and we intersect with the Calabi-Yau hypersurface. Now, this is a bit more involved because there are In this map, these sections are not linearly independent. There will be relations between them, and one has to quotient out by those relations. There are various ways that this can be done. It has been implemented, so it's a bit involved. But I'd like not to go into the details of that. If you're interested, you can ask me about it later. But the basic point is that you can get, in a very similar way as for the complete intersection Calabi-Yau's, you can also for the Kreutzer-Skarke Calabi-Yau's get random points on the Calabi-Yau. And this is then implemented as another point generator in this package that we provide. So how does this, so in summary then, both for the CCs and the Kreutzer-Skarke Calabi-Yau manifolds, this package, CY-metric, provides point generators that give you a sample of random points on the Calabi-Yau that is distributed with respect to a known measure, which is the Fubini-Studio measure in terms of the CC, and it's the Fubini-Studio measure of these PRs that are given by the coordinates that have coordinates that are sections of Kähler cone generators for the Kreutzer-Skarke Calabi-Yau, so it's a bit more involved there, but the principle is the same. So we can test this. So we use these point generating routines, and we train a neural network to find a metric on a Kreutzer-Skarke Calabi-Yau. So this is a particular example. It has two Kähler parameters. We train it on a number of points. We run it for 30 epochs. So this is a bit lower now in numbers because it takes longer to do these things. The point generator routine is a bit more involved. And therefore, in order to run this on my laptop, I reduced the runtime of the experiment a bit. But you see here, so this is just a sort of qualitative result, not a good quantitative result, but you see that what we managed to do is to have a decrease of the Monchampère loss here, so both on the training and validation data, and also the volume it's approaching the true value, which happens to be 20 in this case. It's not there yet, but you can also see that the training and the learning here has not really stopped because the curves have not flattened out yet. So if we would run this longer, which is something that is work in progress, then we believe that we will get the same kind of accuracy as for the CCs. Okay, so let me conclude then. So in summary, what we can do now is that we can machine learn Calabi-Yau metrics on Calabi-Yau manifolds of various types, both from the CC and the Kreutzer-Skarke list. It does not really matter if we have multiple complex and Kähler moduli, because what we do, we can always learn the metric for any manifold by picking a point in the moduli space. The novel features that we have now is that we can deal with these multiple Kähler moduli that was not known before how to do, and that we can also deal with historic ambient spaces. There are lots of things that one could continue doing, as Mike was saying in his talk as well. It's still early days when it comes to developing good machine learning routines for learning Calabi-Yau metrics. There are lots of things that we can test. So one thing is to try to improve the performance of these networks. So the architecture is something one could look at, maybe tune hyperparameters in a different way. So that's a very, very small thing to tune, but still there is work to be done there, perhaps. Then I've told you that we can compute the metric at certain points in moduli space. Of course, learning the moduli dependence of the metric is something that would also be extremely interesting, in particular for the swampland conjectures. And this has been done for complex structure moduli dependence on the quintic in particular by Fabian and collaborators, and also in these two papers that are given here. We can also go on and try to solve or learn the Hermitian-Young-Mills equation. So if we have some bundle over our Calabi-Yau manifold, can we find there are interesting connections on these bundles that we might want to learn from if we look at this in physics. And this is something that we are working on, and I think other groups are also working on. We've also talked about the submanifolds. Computing volumes of non-calibrated submanifolds would be interesting. Generalizing this to situations with flux, The loss functions would have to be updated then, but this has been done, some work in this direction has been done in this work by Fabian and collaborators. Also, a very interesting thing that should be done very soon is to compute compare these kind of results that we find with analytic results of K3 metrics, so going down to Calabi-Yau falls, where there are proposals for what the analytic, so here are the proposals for what the analytic Calabi-Yau metric should be. And there has been some work in this direction, but it's not fully done. And then one could think about other special holonomy manifolds. So with that, let me finish. So I hope I have convinced you, at least to some degree, that machine learning is a good tool to learn Calabi-Yau metrics. And I hope that you are curious to explore this package Calabi-Yau metric, which is available on GitHub and which is written so that it would work together with your favorite computational languages, be it Python, Mathematica, or if you're more familiar to working in Sage. The main functionality of this package is demonstrated in some notebooks that you can run on your laptop and see how these things work. So now it's time to use this for physics, and I hope you will join us in doing so. Thank you.
Thank you very much, Magdalena. We have time for one or two short questions. Thanks for the very nice talk. I have a couple of questions regarding the point sampling.
The point sampling?
Yes. So first question, when the toric scaling weights are very hierarchical, let's say, aren't the number of sections, can they be pretty large sometimes?
Yes, yes. Yeah. Good. So the question was, if I understood correctly, this number of sections that we are using as coordinates for projective spaces can become very large if we have a complicated toric ambient space or more. And that is certainly true. So the dimension of these projective spaces can be big. And that is something that we would have to that slows down the point generating. So I will ask Fabian to interrupt me if I'm saying something that is not true, but the way I understand it, this will slow down the point generating because both we have this then large dimensional spaces where we need to find points, but also when we are finding the relations between these sections, if you would do this using a Grobner basis analysis, for example, that would certainly be very computationally costly if you have a large number of relations to find, so a large dimensional, a large number of sections. So we have sort of a quick workaround for this, which works at a generic point and might be less sensible to that problem, but I think in general, yes, there might be some problem with the efficiency of the metric if we go to more complicated ambient spaces. Or, yeah. Right, that is an interesting question. So the question was, how much does the Fubini-Studio metric deviate from the Calabi-Yau metric if we go to particular points, like a conifold point? It's not something that we have explored. I know of other works by James Gray, and I've forgotten the other person on that paper, I'm sorry, where they are using energy functionals to explore that kind of problem. I'm not sure if anyone has done it using machine learning. I don't know if... so this is, not that I'm aware. It hasn't been explored as far as I'm aware, but it's an interesting question to explore. That's a good question. So far we've been focusing on the nice ones, so the simpler ones. So we're also assuming a favorable toric ambient space, so that the Kähler cone gives us all the generators of H11. Yeah, or give us H11 generators. Yeah.
Let's maybe defer questions to the break if possible, and let's thank Magdalena and both speakers, Magdalena and Mike, for the nice talks in this first session.
Thank you.